Hello everyone! In today's video I am going to demonstrate that the statistical interpretation of quantum mechanics holds true for time-varying wave functions. Quantum mechanics teaches us to think of the probable positions of an electron as defined by a probability density. This time I'm going to call it rho of x. But the theory tells us that this rho of x is nothing but the modulus squared of a function of space and time known as psi, which we call the wave function. The statistical interpretation has several conditions that need to be made in order for us to be able to describe reality through this system. These are known as normalization conditions. The first one says as follows. If we want to find the probability of a particle being at some point A, then we would take the integral of this probability density from 0 to A. If we want to find it over all space, then we're going to take the integral from minus infinity to infinity of the wave function. What should the probability of a particle being over all space? It should be 1, because it's going to be somewhere. The second condition says that the boundary conditions as x approaches either infinity or negative infinity of the wave function should be 0. That's because we cannot continue accumulating area indefinitely. It has to end up at some point, and it has to be equal to 1 for the total area. Knowing these two conditions is that we are going to be able to demonstrate that they hold for time-varying wave functions. So what does it mean for a wave function to be time-dependent? The very definition of psi tells us that its magnitude can change with respect to time. Now we know that psi is a complex function, which means it's going to be composed by some real component and an imaginary component. Similarly, we can establish the relationship with the complex conjugate of psi as simply inverting the sign in the imaginary part. We know this from complex analysis. So our interest of this problem is to demonstrate that the time derivative of the normalization condition over all space should be equal to 0, since the quantity inside this time derivative is supposed to be a constant. The way we are going to do this is first recognize that the modulus square of the wave function is just another way of writing the product of its conjugate with itself. So we're going to replace that in here. The product of the conjugate and the wave function with respect to x, like that. Okay, now I'm going to do a trick here which we need to be careful. Notice that everything inside this bracket is a function of both space and time, but I'm taking a derivative with respect to time. So if I want to move the partial derivative, if I want to move this derivative inside the integral, I need to convert it into a partial derivative of time. Just to recognize that this can also a function of space. So I'm going to do that. Integral partial derivative of the product with respect to x, and now we can just apply the chain rule for these two quantities to get psi star, derivative of psi with respect to t, plus derivative of psi star with respect to t times psi dx. in this expression we have a couple components that we do not recognize yet. This time derivative of psi and the time derivative of its conjugate. The way we are going to get them is using Schrödinger equation, a very useful and fundamental equation in quantum mechanics, which is as follows. Very well. In order to solve for this element that we are interested in, we're just going to divide both sides by I times h. So we get the time derivative of psi is equals to minus h bar over 2mi, second partial derivative of psi with respect to x, plus v over I h bar times psi. Following the rules of complex numbers, we can also find the complex conjugate of this expression by removing those minus signs and changing, I forgot that, as this. This is very convenient now because those are the two terms that we didn't know in this expression. Knowing that, we are going to come here and rewrite it as follows. I'm going to take that time derivative as the first term, which is right here, minus h bar over 2mi, second partial derivative of psi with respect to space, plus v over I h bar psi, all that multiplied by psi star, plus psi multiplied by the partial derivative of psi star, which is right here, remember that this is a minus now, and it ends like that. Now this expression might look a little bit scary, but we see a couple of nice things. The first one is that this term will cancel out with that one when multiplied and distributed. And the second thing is that we have a common factor on both terms, a factor of h bar over 2mi. So in the next step, I'm going to take that factor outside of the integral and we're going to see what is left in here. We are left with, I'm going to take this term first because it's positive. We have second partial derivative of psi star with respect to space times psi minus second partial derivative with respect to space of psi times psi star. Okay, this looks very nice. Now, just to rewrite this in a different way that is more convenient for us, imagine for a second that psi is equals to f and psi star is equals to g. So what I have here would be g double prime f minus f double prime g. Now assume that for no reason at all I add f prime, g prime, and then subtract that same quantity. Now what I have here can be written in the following way. It can be written as f double prime g, f double prime g minus f prime g prime minus f g double prime plus f prime g prime. And this right here looks like, sorry, this should be a plus, looks like two product rules that would correspond to functions that look as this. f g prime minus f prime g. And if they are functions of time, for example, we could rewrite this first initial term as this right there. Translating that to our variables, we get the following nice result. H bar over 2mi times the integral. We extract a space partial derivative, and we are left with psi partial derivative of its conjugate with respect to space minus partial derivative of psi with respect to space times psi conjugate, and dx at the end. Having the expression in this form, we can nicely integrate. This dx is going to cancel out with that one, and this is like we are integrating 1 with respect to this whole thing. As we might know already, the integral of 1 times the integral of 1 with respect to something is equal to the something. So this whole thing summarizes as that something evaluated on the boundaries of the integral, and as we know, those boundaries are from minus infinity to infinity. Here we gotta stop for a second and look up at the normalization condition. It says that the limits of the function at infinity or minus infinity are going to be 0. Therefore, when we put infinity and minus infinity in this equation, the whole thing is going to go to 0. What that means then is that the time derivative of that term we were looking for before is equal to 0, which is exactly what we were hoping to find from our calculations. What this means now is that the statistical interpretation of quantum mechanics holds true for any function that changes with time. And this is a great advantage for us because it allows us to perform many calculations, as well as giving us a mind-bending interpretation of the real world. Thank you for watching.